Hi, my name is Evan Peters. I'm an undergraduate co-op working at the University of Victoria Centre for Aerospace Research up in British Columbia, Canada. This monitor says no signal, is that fine? Yeah, okay. So I'll be talking about our modular Cubesat radio project. These are our sponsors. In particular, I'd like to thank ARDC and the Canadian Space Agency for making this project possible. So our project is aims to be a comprehensive radio system, kind of a drop-in system for Cubesat developers that can be adapted to a wide variety of Cubesat missions. I guess for the more terrestrial enthusiasts here, Cubesat is a class of nanosatellite about the size of a shoebox, typically used in university research programs and aerospace personnel training. So they typically have an emphasis on affordability and ease of deployment. So that's our market that we're targeting, sort of, in a sense. So our scheme includes an SDR, a computer, up to 4 exchangeable RF front-end modules, and other hardware peripheral I/O. It'll be in a PC104 form factor, under 1U volume. That's about 10 by 10 by 30 centimeters. And hardware and software will all be released as open source and open access after development. For this project, we want to emphasize GNU radio compatibility, low component cost, being free of ITAR restrictions, and to flight qualify our hardware all through on SkyAnasat, our upcoming Cubesat. We'll be doing this through a variety of scientific experiments, including ionospheric sounding, and some amateur experiments, such as a DVB-S2 video beacon, CW beacon, and a VHF digipeater. Some background for us: the MCR consortium is headed by the UVic Propagation Laboratory. The PI is Professor Peter Dreesen, who's had a lot of experience in ionospheric research and other software-defined radio projects. The Center for Aerospace Research is a mech-eng facility headed by Professor Afzal Suleiman, which historically worked on unmanned aerial systems and drones, but due to some Canadian Space Agency initiatives, we've now been able to explore the Cubesat space and move into that project. Those projects, including the OrcaSat mission, which was launched in 2022, had a successful mission life of about 120 days and has demonstrated that we have the capabilities for full in-house Cubesat development. And also the undergraduate UVic Satellite Design Club, which works on personnel training through satellite development and interstation development. A side note, this project will be added to our growing repertoire of open source projects, including our UHF dipole antenna, which shortly after we released was pretty quickly adopted by some other Canadian Cubesat developers, so clearly shows demand for these types of projects. Speaking of demand, our motivation, so Cubesat development obviously presents many challenges, but in particular we found that the acquisition or development of radio hardware is often either fiscally or skill-wise outside of the capabilities of many developers, also including international regulations for other countries. This can be a significant challenge. So we're hoping to create a framework that addresses many of these issues, offers full hardware and software adaptability, transparent design, low cost, no ITAR restrictions, easily procured. And the baseline is Cubesat development is typically for research programs and personnel training. So we want to offer a framework that mitigates risk by being flight tested at its core, but still having capabilities for future development and future training with those front-end modules that can be adapted by end users. So yeah, you all know software-defined radio and its capabilities, but some use cases could be repeaters, transponders, beacons, satellite telecommand, or amateur television. The main emphasis here for this slide is just that we hope to expand our representation in other satellite downlink bands. As you can see on the diagram there's quite a lot of UHF, S-band, and X-band satellite representation, but not so much in other bands, which we're hoping to help encourage and foster. For implementation, there'll be a computer board, SDR board, and those front-end modules, 4 of them illustrated here, but you can have as many as you want. These are typically power amplifiers or transverters to target other bands outside of the intermediate frequency that the SDR outputs at HF 10 meter. And yeah, in addition, only the computer board will actually be connected to the PC-104 SAT bus, the rest of the satellite. The rest will all be internal, so it's very much a drop-in-place system, all internal telemetry and all that. So for the computer, we only have a 2-year development timeline, so a fully custom design wasn't feasible. We decided to go for purchasing a system on module. This avoids ball grid array or custom processor sockets, which are difficult to manufacture, often require like x-rays to inspect that they're properly assembled and so on. So to avoid this and decrease that overhead, we selected AMD Korea K24. It meets most of our criteria. And yeah, that's what we're going with there. For software, the main takeaway from this slide is that we will be developing all of the core requirements, such as command processor, telemetry interfaces, and several base flow graphs. But because it's an open source project, end users will obviously be able to create their own flow graphs and peripheral drivers and so on to suit their needs as required. For the SDR, again, 2-year development timeline, so we'll be modifying the Hermes Lite 2. We've had a good experience modifying open source hardware with Orcasat, where we modified OpenLST to suit our needs. This will be a full layout redesign to fit that PC-104 form factor and a slight BOM modifications, but for the large part should have the same operating characteristics as a Hermes Lite 2, which I imagine many of you are familiar with. For buses and interconnects, how the actual modularity is going to work. Each front-end module will have telemetry and control through a small MCU. This will be interacted with the computer through a CAN bus and can both control the module and its capabilities, deactivate certain sections, control which voltage outputs and so on, as well as report telemetry to the larger satellite bus. For power and PTT, each board will be able to be disabled for power conservation. Yeah, this is all straightforward. Same with push-to-talk. If you don't want your power amplifiers running all the time, they're very power hungry, it's good to push-to-talk to only turn them on when required. For TXIF distribution, since it's our frequencies, this was a little more engaged than the digital buses that we've been going over. Typically, so these will all be done through UFL and coax cables connecting the boards. There are other options, such as PNC and so on, but this targets the right frequency range for us and is, again, very affordable, very practical. I will pass through all the modules in the stack by default, but if one module, say, wants to use TX, it will divert the signal into itself, cutting off lower down modules in the stack. This just prevents multiple from receiving or transmitting and any overlap there. Similarly with the LO, since we want duplex communications, we want the LO to be able to go through all front-end modules simultaneously, and we'll just be using an RF splitter with a set 3 dB attenuation per board. Fairly straightforward, again, UFL connectors, but if you wanted like a very high frequency LO, there are more expensive alternatives that are fairly easy to swap in there. For flight demonstration, the MCR will be going on Skynasat, 3 Cubesat being built by students at UVic. It's UVic's submission to the CSA Cubics program and should be launched in SSO orbit in Q1 2026. As I mentioned earlier, we'll have several scientific and amateur research payloads for ionospheric sounding, DVB-S2 video, Digipeater, as well as the CW telemetry that I mentioned earlier. But we will be doing TT&C communication, or telemetry tracking and command for elaboration, communications through our UHF radio that we've already used on Orcasat, just so in case there are any issues, we aren't just dead in the water, as goes with Cubesat development. And we aim for Skynasat to be Canada's first Oscar-designated satellite, should we be successful with our amateur research payloads. For the trans-ionospheric sounding, this will be accomplished through power delay profile measurements down at the long wavelength array in New Mexico, as mentioned in the previous presentation, actually. So we've worked with them before and had success working with them. They'll be gathering our data, and that should offer a 3D map, in a sense, over time of the structure and composition of the ionosphere, which we could correlate to climate change activity over time as well. That said, you don't need a highly complicated long wavelength array for this. For 2D power delay profile, we will be doing a citizen science element where hopefully the ham radio community will be receiving these signals and submitting them to our web-based database and adding to our data gathering. This will be using an HF power amplifier module as one of the front ends modular front ends that I was talking about. There's a plethora of open source designs and so on that we will be drawing from to implement this. The DVB-S2 video beacon on HF 10 meter is an adaptation of the DVB-S2 protocol for use on shortwave frequencies. We've adapted this to use smaller bandwidth than conventional, and has been demonstrated by Robert Swinbank and our investigation to be feasible. This should pose a very rare and interesting experiment for amateur radio operators to investigate. We'll be using just a Raspberry Pi camera too for this. Again, it meets our bandwidth capabilities and is pretty well proven. We'll be using a Greenscube style digipeater to repeat VHF packets on VHF. Since this uses a transverter, it'll demonstrate the frequency conversion of the MCR scheme. And we chose Greenscube because it has much better power efficiency and higher bit rate than typical conventional digipeater approaches. So again, but since Greenscube was fairly successful, we're encouraged that it will be successful as well. And operators have the capability to receive these signals. That'll be using a VHF transverter based on M5 EVT's Hermes Light 2 VHF transverter. Fairly loosely, it'll have the same general block diagram and components, but well, different components, different BOM, but same flow in a sense. Yeah, so again, for these states, we'll only be operating in one state at a time, only one payload active, just to prevent interference. We'll be releasing a schedule for when TT&C will be happening, when the digipeater will be active, when the science payload and so on will be operating. Yeah, so to summarize, we have a repository link there if anyone is interested. It'll also be posted on skynosat.ca shortly, and yeah, we'll be fully flight testing and releasing an SDR board, the system on module mounting board, an HFPA, a VHF transverter, the standardized module template, all the enclosures and mounting hardware. And for software, this will also all be flight qualified except for the AX.25 stuff mentioned in the middle there. Computer and command processor, module telemetry gathering, 30 kilohertz linear transponder, 15 words per minute CW telemetry beacon, the AX.25 telemetry beacon, and a telecommand module, MIPI camera interface, narrowband DVB-S2 beacon, and linear frequency modulated radar beacon that we will be using for our ionospheric sounding. Yeah, that's a fairly quick presentation, but